Welcome back. Alex Wiseman here. If you are continuing from the last screencast on measures of variability, we were actually discussing this histogram when the time ran out. I wasn't watching the time very closely, so we got cut off right at our 15-minute mark. But what we've been doing is we were looking at some of the measures of variability for this set of homework scores from a real class that I taught several years ago at a different university. On statistics. And we can calculate the measures of central tendency, we can calculate the measures of variability, all using the very simple formulas that we have. And we were talking about these distributions and the variability that we saw in them. And we said that, for example, with this Chapter 1 homework, we were looking at a skewed distribution, right? And it was negatively or left skewed. We were saying that it was not a normal distribution, and we were saying that the kurtosis on this was meso, because it's not flat, it's not peaked, it's right in between. And that tells us a little bit about the variability that we have. We noticed on the Chapter 2 homework that we had a significant outlier, which pulled the tail over to the left end. So again, we have a skewed distribution, but we have a larger standard deviation because of this outlier. And we have a very flat or platykurtic distribution, which means that it is also a wider distribution of things. And now we were moving on to the Chapter 3 homework distributions, and again we had some outliers, although now that we have one score over there, but we have some of these other scores sort of moving over that way. It's not quite as much of an outlier anymore. And again, it's left skewed or negatively skewed. Most of the scores are bunched up at the top end. We have a slightly smaller standard deviation than we had before. And remember, this is telling us where or how many points from the mean most of the distribution lies. So the mean is 7.7. That's about right here. So one standard deviation away is essentially 2.5 points in either direction. So if we went 1, 2.5, we'd be here. And if we went 1, 2.5, we'd be here. So 68% of our scores, at least, are going to fall within that range. So that was a little bit of tying up loose ends from the last one. And so here we go talking about some other variability stuff. One of the things that it's nice to do is it's nice to be able to standardize scores, and there's a way of doing that using something called Z-scores. It's literally a standardized score describing how many standard deviations from the mean a score is located. And when it's useful is when you're comparing scores from distributions that have different means and standard deviations. So a very simple way to think about this is you might be looking at, or you might want to compare the results that students had on two different kinds of tests. Maybe one of those tests went from 1 to 10 possible points, and the other one went from 0 to 59 possible points. And so the means, the medians, and the modes would be different for these two distributions. The standard deviations would be different, etc. Right? So you're trying to compare scores, but you're comparing them using the standardized score distributions that are articulated using standard deviations. So how many standard deviations from the mean? And there's a very simple way to convert scores into Z-scores that you could do by hand, or you could build into a calculation that you run in SPSS. And I think it's just important to think about what it is. It's simply the individual score minus the mean divided by the standard deviation. Ta-da! And then you have a Z-score. It's really very straightforward. So suppose a set of scores has a mean of 20.8 and a standard deviation of 4.78. Could you convert the following scores on this variable into standard scores? So the mean equals 20.8 and the standard deviation equals 4.78. And we know that our calculation is individual score minus mean divided by standard deviation. Individual score minus mean divided by standard deviation. So here you go. You have the scores, right? And you have the mean and the standard deviation. So if you take 19 minus 20.8 divided by 4.78, you get negative 0.38. If you have 21 minus 20.8, okay, there are larger numbers that go with this, sorry, 20, 21, anyway. Divided by the standard deviation, you get 0.04. If you have 20 minus 20.8 divided by 4.78, you get negative 0.17. You can see how this goes. We could go through each one of them, and you could calculate that by hand, each one of them, if you wanted to. And this gives us a nice set of standardized scores. And these standardized scores, I'm sorry, I'm going back. These standardized scores are simply a representation of the, where am I? How many standard deviations from the mean a score is located. So this score 19 is negative 0.38 standard deviations from the mean. This score 21 is 0.04 standard deviations from the mean. The score 20 is negative 0.17 standard deviations from the mean. So you can tell where they are in terms of above or below the mean, etc. Okay. So, using the formula for a z-score, could we derive the formula for converting a z-score into a raw score? So here's our z-score formula. All we have to do is use a little bit of algebra. We move the standard deviation over here, right, by multiplying standard deviation by each side. When you multiply it over here, it crosses it out, and you're left with that. And then all you have to do is to add the mean to each side, right? It crosses out here because a negative one and a positive one exists, and all you're left with is the plus. Right? So if you wanted to convert forwards and backwards, you can do that relatively easily. All right, z-scores and probability. We know that 84% of all scores fall below a z-score of +1. Why do we know that? Well, because when we're calculating or looking at our standard distribution, we had 0, 1, 2, 3, -1, -2, -3. A z-score of +1 is right here, right? It's one standard deviation above the mean. So all of this is 84% of all scores, right? You add this up, 34, 34, 12, 2, and then a little bit more. And it all comes out to be 84%. Let me erase my ink. We know that 16% of all scores, therefore, are going to fall above a z-score of +1. Here's 0, here's +1. So everything this direction is going to be 16%. Everything this direction is 84%. These percentages or areas can also easily be seen as representing probabilities of a certain score occurring. Right? So let's start thinking about how probable or how likely it is that a score occurs. Remember, here's our distribution again. Here's how we think about the distribution of cases under the normal curve. And so if something is one standard deviation or higher, the likelihood of it appearing is about 16%. But we have a much greater probability that things will fall around the mean. So what is the proportion of the area under the normal curve that lies beyond any particular score? Right? What are the chances that someone will score higher or lower than a particular score? Well, one, we convert the raw score to units of the standard normal distribution. Those are z-scores. And then we use the z-scores in conjunction with table A. That's table A, right? And there are other tables that are going to be more detailed to determine an area or a proportion of the curve that tells how much of the area under the curve lies beyond our score. It's a fancy way of saying we can figure out percentile rank. It's the percentage of cases up to and including the one in which we're interested. So I don't know about all of you, but if you have grown up in a test-based education system at all, you probably at one point or another have been told during your own educational career what your percentile rank was. And I'm going to guess most of you are high achievers, so your percentile rank was probably 90% or higher, meaning that you scored at or above 90% of the rest of the population. So for example, we have a normal curve. We want to find the percentile rank of a score of 444. It's right here. Okay. Well, what can we do? We can find the percentage of the normal curve that's above a particular score. I'll give you another example. We want to find what percentage is above 120. So we're literally trying to find what percentage of the scores lie above 120. We can find percentage frequency. That's percentage of the sample size that has scores in the area of interest. We can find the probability from that percentage area, which is the probability associated with the percentage area under the normal curve. Right? So we can say, all right, we have a score of 90 and a score of 120. That gives us, when we convert those to Z-scores, a Z of negative 0.63 and a Z of 1.25. So all then we have to do is to find the difference between each of these and the mean and add it together to say the probability of a score lying between 90 and 120 is, what, 23.5 plus 39.5. So we're simply trying to discover what percentage of scores we have to, or what percentage of the scores lie between each of these indicators. Right? So we know between one standard deviation and two standard deviations what it's going to be. And we know we can calculate between an individual score and the mean what it's supposed to be. We can also find deviant scores. These are scores that are so unlikely to occur that they are on the ends. Right? Sorry about this. Dropped some letters out. This is a normal curve, and it's crooked, illustrating the problem of finding the scores that are cutting off the deviant 20% of the distribution. These, in this case, are IQ scores occurring with a probability of 0.20 or less. And that's where we're headed with this. By being able to calculate the area under the curve, and again, you can do this by hand, although we're going to be doing it mostly using our friend SPSS, we can figure out not only what because earlier we were calculating the area between scores, so we were doing this, we can also find the area so deviant or so off from the center that we would consider it abnormal. I'm just going to say abnormal, although I'm not really meaning that in terms of IQ. Right? And instead of adding this area up, we're adding these areas together. So for example, we know that a reading test has a mean of 10 and a standard deviation of 2. Using the normal distribution, what can we do? Well, can we find the percentile rank corresponding to a score of 11.2? We can, because we can calculate the Z-score, which will be the individual score minus the mean divided by the standard deviation. 11.2 minus 10 divided by 2, right? 1.2 divided by 2.6. Right? So we know what the Z-score is. That's the Z. We know that this score is 0.6 standard deviations above the mean. So all we have to do, we know it's we've got 1, 2, 3, 1, 2, 3, here's 0, here's 1, 2, 3. It's 0.6, it's right here. So we can find the area between this score and the mean, and we know that this right here is 50% of the distribution. So it's simply this plus this to get the percentile rank. Oops, hard to read. We're about to end here, so I will pause and come back to you in the next screencast.